Um, Title of my talk, Vendor Agnostic Heterogeneous Computing. How many of you have heard about CUDA, SYCL, and One API? Yeah, Peter and Samir, probably you know better than me about One API, especially Samir. The rough agenda, vendor agnostic computing, SYCL, One API, maybe show some code samples, and then how to migrate your code from CUDA to SYCL. My goal here is to motivate you, if you have some CUDA applications or if you are a HPC engineer, my goal is to motivate you to move away from CUDA to SYCL and become vendor agnostic. And then I'm the program manager at Intel for the migrating to SYCL program. So my target is to enable a large number of CUDA applications migrated from CUDA to SYCL. And then as part of that, we have launched a one-stop shop portal. It has all the resources that you will need to take your CUDA code and move it to SYCL. And then if time permits, we'll look at the Jacobi iterative solver and see how you can automate some of that migration and then what you need to do on top of that automation to do a successful migration. But I'm not going to take too much of the time. I think we had a long day today, so I'll try to keep it as brief as possible. All right. A brief introduction. There was a Turing lecture by Hennessy and Patterson in 2018, and they say that it's a new golden age of computer architecture. There's going to be a Cambrian explosion of novel compute architectures. Now, what does Cambrian explosion mean? It's a theory in evolution that around 500 million years ago, life has exploded in various forms, and most of them have become extinct, and only a few of those that we are seeing survived. So in computer architecture, we're going to see the same, something similar is what they predict. What's the reason? Well, the Moore's law has been driving the computer architecture, the processor architecture for a few decades. Now, Moore's law has slowed down, and Dennard scaling, which talks about power consumption, which says that the power consumption is, which says that the CPUs are going to stay power efficient. Well, the Dennard scaling has slowed down a long time ago. And then that has driven instruction level parallelism and multi-core parallelism, but there is only so much performance, cost, and power benefits that we can get out of the traditional techniques like the instruction level parallelism and the multi-cores. So what came next? The heterogeneous accelerators such as GPUs. Right? Now the GPUs are not confined to one vendor anymore. That's the takeaway that I want to give here. It's not confined to NVIDIA anymore. The HPC GPUs, the GPGPUs that we are using for the high performance computing applications, it's not confined to NVIDIA. The other vendors like AMD and AMD and Intel are also coming up with novel GPU architectures targeting the scientific applications. And it's not just the GPUs. If we look at the Intel portfolio, we have GPUs, FPGAs, neuromorphic processors. Well, they say that neuromorphic processors, there's going to be a winter in the neuromorphic processors. They're not as successful as they were intended to be initially. But we have some AI processors, and we also have blockchain processors, right? So along with this proliferation of these various devices, there is also going to be this capability in the near future to mix and match these processors, these heterogeneous processors, with the general purpose processors. And maybe you would throw in some network components, some interconnect, and some sort of maybe HBM RAM, HBM memory. So somebody is going to come up with a RISC-V processor, somebody is going to come up with some blockchain processor, and then people are going to integrate them and create a custom architecture of their own. So one size doesn't fit all into the future, right? There's going to be this explosion of custom compute architectures. That's the future of computing. Now, what does that imply for us? Well, for me and for few people in the room, scientific programmers, computer scientists, and for computational scientists. What does that mean? Well, on one hand, it's exciting because we are going to have multiple choices for the hardware for our scientific applications. But at the same time, different vendors are going to support different tools, and we're going to have to learn various tools and technologies. There's going to be a lot of maintenance. Developing these scientific applications is hard enough, is challenging enough, and now having to adapt them to the hardware, to each vendor, because the hardware is not standardized, is going to make our lives even harder. So how do we tackle this? How do we automate this multi-vendor development to a certain extent? And how do we create and build an ecosystem around this evolving trend in computer architecture? That's the motivation for SYCL and one API. All right, so what's SYCL? SYCL is a Kronos standard for heterogeneous computing. It's a C++ template-based specification for heterogeneous computing. C++, like any other high-level programming language, it is meant for expressing computation on a general purpose processor, right? It does not have this concept of an accelerator. It does not have this concept of expressing computation that runs on an accelerator and the concept of moving data back and forth between the accelerator and the CPU. And SYCL fills that void. It uses templates. It doesn't add any keywords. And SYCL brings the heterogeneous computing into the realm of C++ without adding any new keywords. It does three things. It picks a device. Q is similar to a stream in CUDA, if you're familiar with CUDA. And then it allows us to do data transfers between the accelerator and the CPU. There are two different data transfer models, USM and USM and buffers. And it's just a matter of choice between USM and buffers. USM is closely resembles CUDA. You have device pointers, you have host pointers, and then shared pointers. So there's not much code change that is needed if you're migrating from CUDA. So if you're migrating your code from CUDA to SYCL, then you may want to go with USM. And both these models allow implicit and explicit data transfers. So with implicit data transfers, you leave it for the compiler. You just express your computation and leave it for the compiler to do the data transfers. So it's more accurate, but then the trade-off is it tends to be not as efficient as explicit data transfers, where you manually take control of the data transfers. And finally, you submit it to a queue and offload the computation to the accelerator. And then we have two forms of scheduling, in order and out of order. In order is simple, and it allows you to debug. So if you have out of order scheduling, which is more efficient, then why use in order? But it helps with debugging. This is a little CUDA to SYCL dictionary. So SYCL introduced new jargon. I don't know why. It would be simpler if it is standardized. However, whatever we call a block in CUDA, it's a work group, thread as a work item, grid, n-dimensional range, ND range, where n can be 1, 2, or 3. And then what we call a kernel, it's a command group. There's a concept of stream, which is called a queue, and then shared memory is called local memory. Cooperative groups were introduced, I think, in CUDA 8, right, to allow synchronization between threads in a warp and threads across a warp. So SYCL also allows similar functionality through subgroups. And then unified shared memory, it's same as unified memory. Graphs there is a open source GitHub link that supports graphs. It's community driven. And then again, the virtual memory usage in CUDA is also not yet supported in SYCL. So it's evolving. A picture is worth 1,000 words. And for us, computer scientists, code sample is worth 1,000 words. So here is a simple SYCL program. We create a queue. There's a sickle header at the top. It's a C++ program. That's a takeaway here. It's very well integrated with C++. There's only one line here that runs on the device, and it is allocating a vector. It's just copying a number to each element in a vector. And that q.submit handler, that's a lambda expression to express computation. We're using buffers here for the data transfers. We're not doing any explicit data transfers, so it's all implicit. All we created is a memory construct for handling memory. And then we print these. So at this point, the data gets transferred back to the host for printing, and it all happens underneath. So we submit this program to a backend, to a runtime that understands sickle, and everything is hidden from the programmer. So if you look at NVIDIA CUDA, it's laser focused on NVIDIA GPUs, and you have new keywords. In comparison, sickle is more C++ like. It's just C++. All right, and if you look at NVIDIA CUDA, it's not just the language is only a small part of it. It's the libraries and the ecosystem around it, right? And that's what one API is for sickle. Sickle is the language, and one API is this ecosystem around it. It's the integration of the libraries, the tools, the debuggers, everything, the debug tools, and the frameworks and so forth. Sickle is gaining traction. There are multiple implementations. The HIP sickle is from AMD, and then Compute CPP, that's from Codeplay. It's closed. It's not open source. And then Intel has what is called DPC++ compiler, which is a sickle compiler, and we also have an open source version of it. So we are here at Open Power Academic Discussion Workgroup, right? So it would be a good gig or a good exercise to take the open source one API compiler and compile it against Power and build it against Power systems, which are widely used in DOE. Samir talked about University of Oregon. So there's plenty of usage of Power 9 systems for scientific applications. There is an Aurora supercomputer that's being built at Oregon, but it's an exascale system, and the exascale system right now from AMD, I think there was a news about 2 weeks ago, it's experiencing almost failures every day, right? Node failures. Being exascale is not easy, right? So what does that imply? That implies that the power systems will be continued to use for quite some time in the DOE labs. And if we can make this one API compiler available on the power systems, I think researchers, DOE researchers will be using it to port their applications, good applications, to sickle. The DPC++ compatibility tool, it's also open source under the name Cyclomatic. So it's a tool that allows automatic migration of CUDA code to sickle. Okay. And the marketing message is it automatically translates 90 to 95% of the CUDA code. But this is an academic discussion group, so not really. But 90 to 95% maybe for simple CUDA code. But for real applications like the DOE scientific libraries, maybe 50 to 60%, and then the remaining 40% of the code requires manual intervention. And it provides some comments on what features to use. It helps to some extent on the unmigrated code as well. All right, a simple vector addition from CUDA to sickle. I hope the code is clear. Okay, in this case, it's a simple vector addition, right? So it does 100% migration from CUDA to sickle. If we use DPCT tool here, if we use the automatic migration tool, it does 100%. If we take one of these NVIDIA CUDA samples and run the DPCT tool, it will do 80 to 90%. And for large libraries, maybe 60%. So the DPCT tool has two main advantages. One, it reduces a lot of typing. And two, it shows this compatible features in sickle. It does this, so you don't have to dig into the sickle manuals to find out what is the equivalent functionality in sickle. It does this automatically, and it may have some bugs, you may have to fix it, but it saves some time. And it's continually evolving. So I'm leading this program and providing feedback to the compatibility tool team so that they can augment the tool. So the tool will get better. And then the profiling, you can profile sickle code with the Nsight, NVIDIA Nsight. You won't get the CUDA runtime API level profiling, but you can see the PTX API calls there. So you should be able to do some one-to-one mapping and do some performance optimizations as well. All right, lastly, let me show this portal. This is a portal that we have launched recently. So that's our principal engineer, James Reinders, talking about vendor agnostic computing and introducing SYCL and one API. So these are the examples that we have identified. These are the example CUDA migrations from outside of Intel across the world. And this is a start. We have listed 5 applications here, but my goal is to build a long SYCL catalog, a CUDA to SYCL catalog. If you look at CUDA catalog, it has around 700 to 1,000 applications. Well, CUDA evolved over 10 to 15 years, 2007, right? This is 15 years. SYCL is relatively new. If you're familiar with OpenCL, then SYCL is an evolution of OpenCL. And we will be expanding this catalog. We will be building this catalog. It's not a one-time launch and forget portal. We are going to maintain it and we are going to update it. And here there are a few samples. There are 3 of these here: Jacobi iterative solver, an odd even merge sort, and a optical flow estimation. We'll be migrating more of these simple CUDA samples, so you'll be easily able to find how to create equivalent functionality for a given CUDA piece of CUDA code. And then this is a call for action. If you port your code, let us know, and we will highlight you here. We'll post a picture and we'll make you famous. That's all I have.
Can we expect you bug reports directly?
Yeah, you can. Well, there is a forum support here, so you can submit the.
I want to email.
Okay, yeah. This is my only work right now to build this ecosystem. So yeah, send it over to me as well. Yes.
So you mentioned the relationship with OpenCL and SYCL. Intel was acquired Altera, which was OpenCL. So are you aware of what is Intel going to be doing moving forward in terms of to support OpenCL or the Altera FPGA, or do you see that it's going to evolve to support SYCL and have FPGA in that umbrella that can put out there?
Yeah, I can actually point you to some links if you send your email. Intel has some tutorials. We have code samples on how to run one API on FPGAs. So yeah, Intel is supporting one API on FPGAs.
So is OpenCL going to be better in that?
OpenCL, that I'm not sure, but I think SYCL is one level above OpenCL. So Intel is focused on SYCL. And whether OpenCL will be supported, I think it will be supported, but the focus is on the SYCL though, and the one API.
Is there any notion that we have a hybrid environment? Because I know that I'm not an FPGA core person myself. I think that is some of the pushback that getting to see is that a lot of things we roll, parallel are not expressible, controllable, OpenCL and signal abstraction perspective. So there's this plan range type of hybrid environment where those are the more rigorous finding requirements that are needed and be able to marry it
with the C++ code. Yeah, yeah. I'm not familiar with the details, but yeah, something like the IP cores, they stay as they are, and then you build your C++ code around them. Yeah. Personally, I felt that using one API on FPGAs, using SYCL on one API on FPGAs, I mean, that's been the holy grail, using some sort of high-level language on FPGAs, right? And the problems and issues are very similar as they were a few years ago. It's not, the compilation is for hours, right? It's not minutes and seconds. And the performance at the end of the day, why would you use FPGAs for performance? To get the performance. And if you're writing in SYCL and if you cannot squeeze the performance, and even the expressing the computation, the expression of computation is, I feel that there is some sort of disconnect between the way we express it in VHDL or Verilog and how you express it in high-level language, right? So. But from programming standpoint, yes, we do support FPGAs, and there are some code samples, there are tutorials, there are, I can forward you some links.
Great.
Any more questions for Chekuri? Okay.
All right, thank you.
Well, as we come to the end of today's ADD workshop, we want to thank you all for coming here today. We want to continue to engage with all of you. Please drop us a line, stop by the Open Power Foundation booth. Let's discuss projects, what you may have for mutual interest, and please let us know how we can help you, how we can help you succeed in your goals. And Ganesan?
Yeah, sure. Thank you all, for being with us today. And certainly, there are people in the morning came here and away now, and afternoon also people who are here. Thank you very much. And it is a great, opportunity for all of you to work with us and see how we can develop the stack. The technology stack as well as the domain stack. The people are offering, big infrastructure, for you all. Just sending one mail, you get an infrastructure, you can start working on chip to solution. That's a concept, the workshop concept from me. And you all can develop chip as well as solution on top of the house. It could be AI or cloud or HPC or any kind of quantum the simulator, anything you can work on. Because we have all kinds of experts available who can help you to develop the skills too.
Yes, and I think that's really a key point over here, a differentiator, that you can have easy access to experts in the area of compilers, runtime systems, networking technologies, data and AI ML technologies, and have access to systems where you can test out your ideas. So I think that access is very valuable and one of the key things that Open Power Foundation is offering.
Sure.
Yes, absolutely.
Okay. Thank you. Yeah. Great show. Thank you. If you are really any good for
Kind of virtual consent form.
No, okay, I think I want to play that Manorat, play that agenda, the agenda which I showcased in the morning here. So group photo should come there, with the agenda. Like
Which one?
the first. Oh, this one only. This one.
Okay.
Yeah.
That's-
Yes. Yeah, we have one.
Is that okay? Should I zoom?
Yeah.
Okay.
Yeah. Yeah, can we? Please come here. For the little one. Oh. So I'm sorry. That's 700. So maybe, no, let's not do this. You play the other video, the other one, not the photo. The other second page. Zoom that, that's it. That's it. This is enough. Okay. Where do you want us to stand? Yeah. You want to go right now. Don't get a halo. So we're not all. The background.